So I hope my screen is visible to everyone. So I'll just cover up the remaining things, whatever we are left out with, and then we'll start up with the examples what we have to run. And earlier we have discussed about the other design as well. On the Friday, actually, we have discussed on 3x3 patch antenna, right? There was a small correction in the design, which I'll go through these steps and you can clearly understand it, how exactly it is worked out. So before that, I'll just give you a brief glance on what kind of solvers are left out and what are the additional benefits by taking ESI CEM ONE software for electromagnetic simulation. So high frequency solver, this solver is exclusively used for electrically large structures. Like if you want to analyze the performance of a radome, or else if you want to analyze the performance of a complex shapes, it basically uses the technique of physical optics. Physical optics is nothing but it's completely based on the theory of diffraction and reflection. It's based on diffraction, how exactly the light is diffracting on the particular structure, and what is the scattering fields you're getting it. And similarly, the things what we have in this particular high frequency simulation is it's like phase scattering and phase scattering with physical optics, and wedge scattering is reduced from equivalent equations. So if you're taking a structure, like if you're taking a big aircraft, so big aircraft you want to simulate with this physical optics, that is high frequency solver. What you can do is actually it completely solves the problem in terms of optical illumination. So it produces illuminated beams on the top of the particular structure in all directions, based on which you'll be getting facets and wedges. So facets and wedges will be analyzed based on the multiple order of reflections, and you will be completely analyzing the structure analysis with respect to the currents, surface currents which are passing through the object, and similarly you have first order reflection, second order reflection, triple order reflections, etc., based on which the complete performance of the complete structure would be analyzed. So in order to manage directly, the edge diffraction, simple double reflections followed by edge diffraction are also taken into account. So high frequency solver, it's nothing but it's based on the optical theory. So you will be projecting optical beams on all the directions of your structure based on your reflections, based on your diffractions and edge currents what you're getting out on the surface. You will be actually evaluating the performance of that particular structure. And coming to hybrid solvers, we can also use a combination of solvers like MOM, MLFM, PO, FDTD, PO based on the application. For example, if you have an application where you have to go ahead with, you want to mount the antenna on structure, and you want to analyze the performance of interference. How exactly one antenna is interfering with the other antenna. In that case, what we can do is for structure we can take one solver, and similarly for antenna we can take one solver. For example, if your antenna is electrically very small, that is in between the range of 0.1 lambda to 10 lambda, then you can directly go ahead with MOM, and physical optics will be actually useful for the structure whatever you're using for analyzing. In the similar fashion, you have FDTD, PO, where the main antenna will be analyzed with FDTD, and PO is for complete structure what you're using. And then we have hybrid EFI, CFI equations, which are used for reducing number of iterations and solve the problem at the earliest. So these are some of the hybrid solvers which are utilized in ESI CEM ONE. And some unique features in CEM ONE, what we have is all EMC relevant features in single shared model. Importation of industrial CAD model, including the network featuring hundreds of bundles and thousands of wires also you can incorporate. User control on meshing. So this is one of the good feature in ESI Visual CEM software, where you can control the mesh size and even the quality check options, which actually tells you how quality your mesh is all about, and how can you improve the quality of your mesh also. And we have hybridization techniques and MDMM, which is nothing but multi-domain method. So if time permits, we'll also go with one example on this. And spherical wave expansion, we've already covered the 3x3 patch antenna what we have done, right? It's a spherical wave expansion what we have. And virtual anechoic chamber, you can also prepare a very large simulation case where you can prepare n number of elements, n number of unknowns with a virtual anechoic chamber. So we have micro basis functions. Micro basis functions are exclusively used if you want to get started with 2D arrays. 2D arrays like M cross N antenna arrays. So we have some example set for 2D arrays also, which you can take it, and you can build your own antennas on your own. So this particular micro basis function is a very easier function to actually get started with the 2D array implementation. So you can use a spherical wave expansion combination and this particular micro basis function in order to create a very big large antenna array, and you can incorporate that into a radome or any other structures whichever is required. And multi-domain multi method is nothing but domain decomposition technique. So in a simple words, what we can say is it divides the complete problem into subparts. Each and every subpart is individually solved, and together the results will be combined, and then you'll be getting the final results. So that's what happens in MDMM. So installed antenna performance, antenna coupling, cavity RCS of air intakes and exhausts, RCS of installed antennas, waveguides, these all comes under your MDMM technique. Can be easily solved by using MDMM technique. So the idea behind this technique is decomposing the complete problem into subparts and evaluate all the parts individually and then provide the solution at the earliest. That is what is a major idea of this MDMM to solve about. Similarly, benefits, it's a most efficient solver which can be used with MOM, FAM, FEM, MLFMM and PO also. So you can make use of this particular antenna with this particular technique with all the solvers and reduce the computational size because we are dividing the complex problem into subparts and we are trying to analyze it. So it reduces the things. And similarly, optimal efficiency of MLFMM by extracting the resonant parts such as cavities. So if you're using MLFMM in conjunction with your MDMM technique, you will be getting the optimal efficiency from the output. And similarly, in case of any design changes, only the modified domains need to be recomputed. There is no need of computing the problem from scratch to the end. So whichever part you are modifying, that part will be evaluated. Remaining parts will be as it is put, and thereby you will be saving a lot amount of time. This is one of the unique technique which is used in ASI in order to solve the electromagnetic problems in the defense and even the industries also. So reduce the simulation of swarm antenna. There is a design case which is nothing but swarm antenna, which is for Swedish defense. They have built it. So it solved almost like 8 times faster when we are using MDMM technique. And high level parallelism is also available with this MDMM. So these are some of the benefits. We'll also try to look at the design cases. So this all comes under your product overview. So which solver to use in which kind of circumstances. So you can see it's like physical optics for higher electrical size, MLFM which is lower electrical size when compared to the physical optics, MOM even furthermore lower electrical size, FEM even the less electrical size, FDTD for some circuits, MTL is for if you want to solve some cabling kind of thing, you can go ahead with that. FEM finite element method, MOM is almost the same. You can go ahead with whatever method you want to use. So this is nothing but your graph chart based on the complexity, based on the electrical size, which particular solver you have to use. That's what is a product overview, what I can show it to you. And this remaining part are the examples and the results what we have, which I'll show it to you in the later phase. Before that, we'll just get started with the thing. So one correction what was required is